Welcome to Thermodynamics lecture series. In the present video, we will discuss the JNTUH previous problems on first law of thermodynamics of closed system. Let's see the first problem. When a closed system executes a certain non-flow process, have the work and heat interactions. Those values per degree rise in temperature are given by the relations dW by dt equal to 4 minus 0.08 T kilojoule per Kelvin and dQ by dt equal to 1.00 kilojoule per Kelvin. Then calculate the increase or decrease in the internal energy of the system if it is to operate between the temperature limits of 200 degrees Celsius and 500 degrees Celsius. Let's see the solution. First, we have to observe the given data. So here it is, the given system is closed system, and so we'll give the relations of the dW by dt, which is equal to the 4 minus 0.08 T kilojoule per Kelvin, and dQ by dt also given 1.0 kilojoule per Kelvin. So next we have to calculate the increase or decrease change in internal energy. You have to determine, that is del U we have to determine, and moreover it is given the temperature limits. So let's consider T1 equal to the 200 degrees Celsius and T2 equal to the 500 degrees Celsius. So first we have to apply the first law of thermodynamics for closed system. We know that one, dQ equal to the du plus dW. So from this relation we can be write down the du equal to dQ minus dW. So then differentiate with respect to the temperature, then equation will become the du by dt equal to dQ by dt minus dW by dt. So in the data it is given the dQ by dt, and moreover it is given the dW by dt. Then you have to substitute these values, then we will get the du by dt equal to the dQ by dt is the 1 and dW by dt equal to the 4 minus 0.08 T. Then it will become the du by dt equal to the minus 3 plus 0.08 T. So next we have to integrate between the temperature limits. So then del U equal to the integration of T2 to T1, that is the 500 to 200, minus 3 plus 0.08 T dt. Then integrating we will get the del U equal to the, so 3 minus 3 is the constant, then minus 3T, and T will become the T square by 2, then it will become the, so 0.04. So del U equal to the minus 3T plus 0.04 T square. Limits are the 500 to 200. Then substitute the limits. First we have to substitute when the T equal to the 500, and this will become the 3 into minus 3 into 500 plus 0.04 into 500 square. So it will become the 8500. Similarly, at T equal to the 200 degrees Celsius, then it will become the 1000. So then del U equal to the 8500 minus 1000, it will become the del U equal to the 7500 kilojoules. So here it is the positive change in internal energy, then increase in internal energy of the 7500 kilojoules. So this is the solution. So next I have to go for the another problem. Let's see the problem. A mass of 1.5 kg of air is compressed in a quasi-static process from 0.1 megapascal to a final pressure 0.7 megapascal By following the law, PV to the power 1.75 equal to the constant. The initial density of air is 1.16 kg per meter cube. Find the final density, work done by the piston during compression and heat transfer. So let's see the solution. So first we have to write down the given data. So here it is given the a mass of 1.5 kg of air. So given the mass of the air, let's consider small m equal to the 1.5 kg, and here it is given the initial pressure as well as the final pressure. Let's consider the initial pressure is the 0.1 megapascal, which is equal to the 100 kilopascal. Similarly, final pressure P2 equal to the 0.7 megapascal, which is equal to the 700 kilopascal. And the following law is the polytropic process, which is the relation is the PV to the power 1.75 equal to the constant, and here polytropic index N equal to the 1.75, and also given the initial density of the air, which is equal to the 1.16 kg per meter cube. Then we have to determine the final density. Let's consider rho 2, work done W, and we have to determine the heat transfer Q. So let's see the solution. So first we have to determine the final density. We know the density relation is the rho equal to m by v. So here initial density is given, that is the rho 1 equal to the 1.16 kg per meter cube. So then we have to determine the rho 2 m by v2 we have to determine. So for the determination of the final density we need the v2 value, but in the data it is not given the v1 as well as the v2. So first we have to determine the v1 value by using the rho 1 equation. So rho 1 equal to m by v1, then v1 equal to the m by rho 1. So m is given as well as the rho 1 also given. So which is equal to the v1 equal to the m is the 1.5 and rho 1 is the 1.16, then v1 equal to the 1.5 divided by 1.16, which is equal to the 1.293 meter cube. So we know the v1 value, then we have to determine the v2 value. So for this one I have to use the polytropic process law, that is the PV power n equal to the constant, then P1 V1 n equal to the P2 V2 n. So from this relation we can be write as V2 by V1 equal to the P1 by P2 whole to the power 1 by n. So here we have to determine the V2 value. So we know the V1, P1 and P2, and also n value also we know. Then substitute all these values. Then V2 equal to V1 into 1.293 into, so P1 by P2 to the power 1 by n. So which is equal to the 100 divided by 700 whole to the power 1 divided by 1.75. So from this we will get the V2 value is 0.425 meter cube. So we know the V2 value. Then we have to determine the rho 2. So rho 2 equal to m by V2. We know the m value as well as V2 value, substitute, which is equal to the 1.5 divided by 0.425. Then rho 2 equal to the 3.53 kg per meter cubed. So we determine the final density rho 2. Next we have to determine the work done W. So we know the in the polytropic process work done W equal to P1 V1 minus P2 V2 divided by n minus 1. So P1 we know 100, V1 we know 1.293, P2 we know 700, and V2 we know V2 value is 0.425 and n value is the 1.75. Substitute all the values, so we will get the W equal to 100 into 1.293 minus 700 into 0.425 divided by 1.75 minus 1. then we will get the minus 224 kilojoules. So here negative symbol indicating that the process is compression. So compression work we are doing, then work done by the piston on air, which is equal to the 224.3 kilojoules. So we determine the final density as well as the work done. So next we will determine the heat transfer Q. So for this one, I have to applying the first law of thermodynamics, that is Q equal to del U plus W. So here W we know that is minus 224 kilojoules, but we don't know the del U. So in change in internal energy for the air is del U equal to the mCv T2 minus T1. Here we know m value 1.5, T2 and T1. So in the data it is not given the temperature values. So have to determine the T2 value and T1 value and CV value. So CV value we know for the air. So first we have to determine the T1 value. For this one I have to use the P1 V1 equal to the MR T1 relation. So here we know P1 value, V1 value, M value and R value we know and T1 value. So we know for the air Cp equal to the 1.005 kilojoule per kg Kelvin and Cv value is the 0.718 kilojoule per kg Kelvin. R value is the 0.287 kilojoule per kg Kelvin and gamma is the 1.4. So to determination of the T1 value, we know P1, V1, M and R. Substitute all these values, we will get the T1 equal to 300.3 kelvins. So we know the T1 value. Next we have to determine the T2 value. So the process is the polytropic process. In the previous lectures we discussed the for the polytropic process relations between the temperature and pressure, that is the T2 by T1 equal to P2 by P1 whole to the power n minus 1 divided by n. Here we know T1 value, P2 value, P1 value, n value. Then substitute all these values. We will get the T2 equal to the 690.7 kelvins. So we determine the T1 value, T2 value and we know CV value for the air also and M also we know. Then substitute all these values. So we will get the change in internal energy equal to the M is the 1.5, CV value is the 0.718 kilojoule per kg Kelvin and temperature T2 is the 690.7 and T1 is the 300.3. Substitute all these values, we will get the change in internal energy is the 420.5 kilojoules. So we know the change in internal energy and also work done. Then from the first law of thermodynamics, Q equal to del U plus W. Then del U is the 420.5 and W is the minus 224. Substitute, we will get the Q equal to the 196.2 kilojoules. So this is the solution. So next we have to look for the another problem. So let's see the problem. Air occupies a space of 0.3 meter cube at a pressure of 2 bar and at a temperature of 77 degrees Celsius. It is heated at a constant volume until the pressure is 7 bar. Estimate the final temperature and change in internal energy. So let's see the solution. Before that, we have to see the given data. Here the process is the constant volume process and given the volume is given. So volume is the constant volume which is equal to V1 equal to V2 equal to the V. So initial volume and final volume, whatever V1 equal to V2 equal to V, which is equal to the 0.3 meter cube. And initial pressure is given the 2 bar. Let's consider P1 equal to the 2 bar. So which is equal to the 200 kilopascal. And initial temperature also given, that is the 77 degrees Celsius, which is equal to the 77 plus 273, which is equal to the 350 Kelvin. And the process is given the constant volume process. Final pressure is given P2 equal to the 7 bar, which is equal to the 7 into 10 to the power 5 Newton per meter square. That is also we can be written as 700 kilopascal. So then we have to determine the final temperature. Let's consider the T2, and we have to determine the change in internal energy. Okay, so let's see the solution. So constant volume process. So in the constant volume process, we know PV equal to the MRT, and V and M and R is the constant. Then P is directly proportional to the T. Then P1 by T1 equal to the P2 by T2. So how to determine the final temperature? So in the data given the P1 and P2 and also given the T1. Then substitute all these values. Then T2 equal to T1 into P2 by P1, which is equal to the T2 equal to 350 into 700 by 200. So which is equal to the 1225 kelvins. So this is the T2 value. So next we have to determine the change in internal energy. Change in internal energy del U equal to mCV T2 minus T1. So M is not given in the data, we have to determine. CV value we know for the air, and T1 is given data and T2 we determine. So first we have to determine the M value. So for this one we have to use the ideal gas equation PV equal to the MRT. So from this one M equal to the PV by RT, and this can be written as the P1 V1, but V is the constant, V1 equal to V2 equal to V, and divided by RT1. So P1 V by RT1. So P1 value we know, so 200 kilopascal, and V value we know, and R value, so R value also we know in for the air, and T1 value also we know. So R value for the air is the 0.287 kilojoule per kg Kelvin. Then substitute all these values. M equal to the P1 200, 200 into V is the 0.3 divided by R value is the 0.287 into T1. T1 is given in the data 350. Then M equal to the 0.597 kg. So now we know the M value and CV value, T2 value and T1 value. Substitute all these values, then change in internal energy equal to the 0.597 into 0.718 into, so 1225 minus 350, which is equal to the 350 kilojoules. So this is the solution, and thank you.